Good morning, everyone. Welcome. Today, we are going deep into another foundational topic in thermodynamics, that is energy transfer, displacement, work transfer, and power. Understanding how energy moves or it is converted and utilized is absolutely crucial for anyone working with thermodynamic systems. Any type of mechanical or electrical energy in which the energy transfer occurs is very much important to understand from thermodynamic point of view. Energy transfer is the lifeblood of any device or process that involves doing work or producing heat. It's the mechanism by which energy moves from one place to another, transforming from one form to another along the way. A comprehensive understanding of energy transfer is essential for analyzing and designing everything from the simplest lever to the most complex power plant. In this lecture, we will systematically explore these interconnected concepts. Specifically, we will cover what is energy transfer. We will start with a clear and concise definition of energy transfer, establishing the fundamental principle that governs its behavior. We will examine the different ways energy can be transferred and introduce a key concept that we will explore in more detail. Then we will see the types of energy transfer. We will go deep into different modes of energy transfer. This will include exploring mechanical energy transfer, heat energy transfer, and briefly the energy transfer via waves. We will provide example of each type of transfer and discuss the factors that influence their effectiveness. We will see the displacement work transfer. This is a specific and extremely important type of work transfer. We will develop the mathematical expression for displacement work transfer and explain how it relates to pressure, volume, and the movement of system boundaries. Finally, we will see the definition and calculation of power. We will turn our attention to the concept of power, which is the rate at which energy is transferred or transformed. We will define power, discuss its units, and learn how to calculate it in various scenarios. By the end of this session, you will have a solid understanding of how energy is transferred between systems and how work and power are quantified. This knowledge will empower you to analyze and design a wide range of engineering systems and will provide a strong foundation for more advanced topics in thermodynamics and related fields. So let's get started and unlock the secrets of energy transfer. Let's begin by establishing a clear understanding of what we mean by energy transfer in context of thermodynamics and related field. Energy transfer is the process by which energy moves from one system or objects to another. This transfer often involves a change in the form of the energy itself. It's a dynamic process, not a static one. Energy is in motion, changing location and potentially changing the form as it moves. To truly grasp the concept of energy transfer, we need to consider some key underlying principles. So the first principle is the first law of thermodynamics. It is the cornerstone of energy transfer in the first law of thermodynamics. Just wait. So sorry for disturbance. Let's move on this concept. Okay, so now we were discussing the first law of thermodynamics, which is the cornerstone of energy transfer in thermodynamics. This law states that the energy cannot be created nor destroyed. Instead, the energy can only be transformed from one form to another or transferred from one system to another. The total amount of energy in an isolated system remains constant. This principle dictates that the energy transfer is a conservation process. Energy is simply moving around and changing its appearance, not disappearing or appearing out of nowhere. Now, also, the energy transfer can occur through a variety of different mechanisms. The primary mechanism we will focus on today are the mechanical transfer, which we commonly call as a work, heat transfer, and energy transfer via waves. Each of these mechanisms operates according to different physical principles and is relevant in different types of systems. To illustrate the concept of energy transfer, consider a simple example, pushing a car. When you push a car, you are converting chemical energy stored in your body, delivered from the food you eat, into mechanical energy. This mechanical energy is then transferred to the car, causing it to move. The energy is being transformed, that is chemical to mechanical, and transferred from your body to the car. Now that we have established a definition of energy transfer and its key principles, let's move on to discussing the different types of energy transfer in more detail. We will explore the mechanism involved in each type of transfer and provide examples of how they occur in various systems. Let's now go deep into the fundamental and readily observable form of energy transfer, that is mechanical energy transfer. Mechanical energy transfer involves the transfer of energy through the application of forces that causes movement or displacement of object. This is the type of energy transfer that we directly experience in our day-to-day lives, and that is central to the operation of countless machines. The defining characteristics of mechanical energy transfer is that it involves a force acting over a distance. When a force causes an object to move, energy is transferred from the source of the force to the object. This transfer of energy results in a change in the object's kinetic energy. If its speed changes, or its potential energy if its position changes. To illustrate this concept, let's consider the example of a quarterback throwing a football. The quarterback uses the muscles in his arms to exert a force on the football. This force acts over a distance and the quarterback arms moves, transferring the energy from the quarterback's body to the football. As a result, the football gains a kinetic energy and is propelled through the air. The stored or the energy initially stored chemically within the quarterback's muscle is converted into kinetic energy of the football. Mechanical energy transfer is also fundamental to the operation of many machines, such as engines and turbines. In these machines, mechanical energy is transferred through moving parts such as piston, connecting rods, gears, and rotating shaft. For example, in an internal combustion engine, the expanding gases inside the cylinder exerts a force on the piston, causing it to move. This movement of the piston transfers energy to the crankshaft, which then transmits the energy to the wheels of the vehicle. Mechanical energy transfer is a key concept in both physics and engineering because it provides us with a framework for understanding how force interacts with the object to produce motion. It is the foundation upon which we build our understanding of machines, mechanics, and the dynamics of moving systems. Now, let's shift our attention to another crucial form of energy transfer, that is heat energy transfer. Energy transfer is the process by which thermal energy moves from one system or object to another due to a temperature difference. It's a fundamental phenomena that governs the behavior of countless physical systems and engineering devices. Heat transfer always occurs spontaneously from a region of high temperature to a region of lower temperature. This is a consequence of the second law of thermodynamics, which dictates the direction of spontaneous process. There are three primary modes of heat transfer. First is the conduction. The conduction is the transfer of heat through a material by direct contact. It occurs due to the interaction of molecules within the material. Hotter molecules vibrate more rigorously and transfer some of their energy to neighboring cooler molecules through collisions. An example is a metal rod heated at one end, transferring heat to the other end. The convection is the transfer of heat through the movement of fluids, liquids, or gases. When a fluid is heated, it expands and becomes less dense, causing it to rise. Cooler, denser fluid then sinks to take its place, creating a circulating current that transfers heat. An example is warm air rising and cool air sinking to the bottom of a room. Third important heat transfer is radiation heat transfer. Radiation is the transfer of heat through electromagnetic waves. Unlike conduction and convection, radiation do not require a medium to propagate. Energy can be transferred through empty space via electromagnetic radiation. An example is the sun heating the Earth's surface. To illustrate heat transfer, consider the example of a block sliding down a slope. As the block slides, its potential energy due to the height is converted into kinetic energy due to motion. However, due to friction between the block and the slope, some of its kinetic energy is converted into thermal energy, increasing the temperature of both the block and the slope. This thermal energy is then dissipated into the surrounding environment through the heat transfer mechanism. Understanding heat transfer is essential for a wide range of engineering applications, including the design of heat exchangers, air conditioning systems, and engine cooling systems, and insulation of materials. By controlling heat transfer, engineers can optimize the performance and efficiency of these systems. In addition to mechanical and heat energy transfer, energy can also be transferred or transferred through waves. This form of energy transfer is often less common but just as important as playing a critical role in various technologies and natural phenomena. Wave energy transfer involves the propagation of energy through a medium or even through a vacuum in case of electromagnetic waves via oscillating disturbances. The medium itself doesn't necessarily move over long distance. Instead, it is the disturbance that carries the energy. Here are some key examples of wave energy transfer. First one is the sound waves. Sound waves are mechanical waves that travel through a medium such as air, water, or solid by causing the particles in the medium to vibrate. These vibrations carry energy from the source of the sound to the listener's ear. The louder the sound, the greater the energy being transferred by the sound waves. Next is the electromagnetic waves. Electromagnetic waves such as light waves, radio waves, microwaves, X-rays, and gamma rays are disturbances in electric and magnetic fields. Unlike sound waves, electromagnetic waves do not require a medium to propagate and can travel through a vacuum. These waves carry energy in form of photons. The higher the frequency of electromagnetic waves, the greater the energy carried by these photons. Now, wave energy transfer is essential to a wide variety of technologies and applications. Consider one application as telecommunication, in which radio waves and microwaves are used to transmit information over long distances in telecommunication systems. Next is medical imaging. X-rays and ultrasound waves are used in medical imaging to create images of the internal structure of the body. Next one is the renewable energy. Wave power generation harnesses the energy of oceans to generate electricity. Solar energy relies on electromagnetic radiations from the sun. While the specific of wave energy transfer can be complex, the underlying principle is the same. Energy is being transported from one location to another by means of propagating disturbances. Now that we have covered various forms of energy transfer, let's move on to the specific and important type of energy transfer, that is displacement work transfer. Let's now focus on a particularly important type of work transfer, commonly called as a displacement work. Understanding displacement work is essential for analyzing the systems where the volume changes due to the movement of a boundary, such as a piston cylinder devices. In most general sense, work is done whenever a force causes an object to move over a distance. It's a transfer of energy that results from a force acting through a displacement. This means that the work requires both a force and a displacement. If there is a force but no displacement, or a displacement but no force, then no work is done. The mathematical expression for work is given by W is equal to force multiplied by distance multiplied by cos of theta, where W is the work done, which is typically in joules. F is the magnitude of the applied force, typically measured in newtons. D is magnitude of the displacement, typically measured in meters. And theta is the angle between the force vector and the displacement vector. The term cos theta accounts for the fact that only the component of the force that is parallel to the displacement contributes to the work done. If the force is applied in the same direction as the displacement, when the theta is equal to 0, then cos of theta is equal to 1, and the equation simplifies to W is equal to F multiplied by D. However, if the force is applied perpendicular to the displacement when the theta is 90 degrees, the cos of theta value becomes 0 and no work is done. To illustrate this, consider the example of pushing a box across a floor. If you apply a force to the box and the box moves, then you are doing a work on the box. The amount of work done depends on the magnitude of force you apply, the distance the box moves, and the angle between the force and the direction of motion. Now consider the pushing against a solid, immovable wall. You may exert a significant force, but because the wall doesn't move, there is no displacement, and therefore no work is being done on the wall. The force you apply is not transferring energy. This equation for work is fundamental in physics and engineering for calculating energy transfer in mechanical systems. It provides a quantitative way to analyze how forces cause motion and how energy is transferred in the process. Now that we have a solid understanding of work, let's move on the concept of power, which describes the rate at which work is done. Let's now turn our attention to the concept of power. While work tells us how much energy is transferred, power tells us how quickly that energy is transferred. Power is defined as the rate at which work is done, or equivalently the rate at which energy is transferred or transformed from one time. It's a measure of how quickly energy is being used or produced. The mathematical expression for the power is given by P is equal to work divided by time, where P is the power typically in watts, W is the work done or the energy transferred typically in joules, and T is the time taken to do the work or transfer the energy typically measured in seconds. From this equation, we can see that the power is directly proportional to the amount of work done and inversely proportional to the time taken. This means that a system that does not or does a lot of work in a short amount of time has high power output, while a system that does the same amount of work over a longer period of time has a lower power output. Here's a key insight about a power. A system with high power can do work faster than a system with a lower power. For example, consider two electric motors, one with a power rating of 1000 watts and the other with a power rating of 500 watts. The 1000 watt motor can do twice as fast as 500 watt motor. This means that it can lift a heavier load, accelerate a load more quickly, or perform a task in half the time. Power is a critical parameter in many engineering applications, as it determines the performance and capability of machines and devices. It's important to consider both the amount of work that needs to be done and the rate at which it needs to be done when selecting or designing a system. Now let's explore another way to express power, particularly in context of mechanical systems. In addition to defining power as a rate at which work is done, we can also express power in terms of force and velocity. This formulation is particularly useful when analyzing mechanical systems where force is causing an object to move at a certain velocity. This relationship between power, force, and velocity is given by the following equation, where P is equal to force multiplied by velocity. P is the power, F is the force applied, and V is the velocity of the object in the direction of force, and is typically measured in meters per second. This equation tells us that the power required to move an object is equal to the product of force applied to the object and the object's velocity in the direction of force. Let's consider the example of a moving car. The power delivered to the wheels of a car is determined by the force applied to the wheels by the engine and the car velocity. A stronger engine is capable of generating a high force output and can deliver more power to the wheels. This allows the car to accelerate faster and to maintain its speed when climbing hills or overcoming air resistance. This equation is particularly useful for analyzing power in a wide variety or a wide range of mechanical systems, including engines, motors, pumps, and turbines. It allows us to directly relate the force exerted by a system to the velocity it produces and the power it consumes or generates. It's also helpful because it gives us a way to analyze the instantaneous power. The equation P is equal to W by T gives us the average power. But the equation P is equal to F multiplied by V allows us to determine power at a single point in time t. It's also important to note that this equation assumes that the force and velocity are in the same direction. If the force and velocity are not in the same direction, then we need to take the component of force that is parallel to the velocity, similar to that we discussed with the work. By understanding the relationship between the power, force, and velocity, we can gain a valuable insight into the performance and efficiency of various mechanical systems. Now, coming on to the summary of the today's session, we will take few moments to summarize the concepts that we have learned today's session. So in today's session, we have seen what is energy transfer, work, and power. These concepts are absolutely fundamental for analyzing and designing a wide range of engineering systems. The first one is the energy transfer. We have learned that the energy transfer occurs through various mechanisms, including mechanical transfer, involving the movement of objects and application of forces. Next is the heat transfer, in which conduction, convection, and radiation modes of heat transfer, which are driven by the temperature difference. Finally, we have seen the wave transfer through sound waves and electromagnetic waves. In these ways, the energy transfer occurs. We have seen what is the work transfer. Work transfer, specifically the displacement work, which is given by the equation W is equal to F multiplied by D multiplied by cos of theta. And work is done only when the force causes a displacement. If there is no movement or displacement, no work is done regardless of magnitude of the force applied. Then we have seen the power. Power is the rate at which work is done or the rate at which energy is transferred. It can be expressed as P is equal to F multiplied by V, where the power determines how quickly the work is done or how quickly the energy is transferred. A higher power rating indicates a greater capacity to perform work in a shorter amount of time. Understanding this concept is critical for designing and analyzing a wide range of systems, including machines, from simple levers to complex robotics, engines, internal combustion engines, jet engines, etc., electrical systems, that is motor, generator, and power grids. By applying the principles of energy transfer, work, and power, engineers can optimize the performance, efficiency, and reliability of these systems. In short, a solid grasp of these fundamental concepts is essential for analyzing and improving the energy efficiency in a wide range of engineering applications. That concludes our lecture for today. Thank you very much for your attention and participation. I hope you found this session informative. I am now happy to answer any questions you may have. Please feel free to drop me an email. Thank you.